Hello. So far we have discussed about several public key cryptographic schemes for encryption mostly, and discrete logarithm ciphers for key exchange and encryption as well. And today we are going to discuss about digital signatures. So when I was talking about RSA, I mentioned that RSA can also be used as a signature scheme. So today we are going to discuss about digital signatures in detail. So before talking about the mathematical things about digital signatures, let's have a little bit of understanding. What are the signatures? Why do we use them? Kind of things. So normally signatures are used to provide integrity or authenticate the origin of the document. So if I am publishing your results, I am putting my signature in the result sheet and put it in the notice board. So because of my signature, you can trust that this is coming from the lecturer in charge. And also in our certificates, paper certificates, we have signatures from several authorized people. So because of that signature, that document is going to be valid. Signatures are used for provide the authentication, origin authentication, integrity, something like that. So in digital signatures, I can say we can achieve the same thing, but in a form of digital. Digital means here we use a kind of a mathematical formula, and through that we provide that trust into the document. I can show a simple example about how to use digital signatures in using for our PDF files. So if you have a PDF document, let's say this one, this is the previous assignment I gave you. Let's say I need to put a digital signature for this document. So I have opened this using Adobe Reader. So in Adobe Reader we have option here, fill and sign. There we can choose place signature option and then place select a place to put the signature, and here to this point we can add a signature. So this is not just adding something like some image of my signature. It is not like that. What it does is, so sign as we can, so these are the digital signatures I have created and saved here, put here. I can sign as Janaka. So if I sign like that, I will show you. Okay, so now it asks for a password I used for that. I can sign and I can copy, I can save. So what it does is, now it puts a tag saying that this document is digitally signed. Here you can see there is something called at least one signature has problems, because there is no way to verify this signature, because there is no signature verification list published in internet. So that should be done by certificate authority, but here I just created my own certificate, and using that I just create a signature, but this signature, the certificate revocation list is not in the internet. That's why it says like that. But when you click on this signature, you can check the signature properties. So it says here there's summary about the signature and the time and date of the signature created, and you can see the information about the certificate which is used to create the signature. So here this is the root certificate. I created that, and this is the sub certificate from that root, and from this certificate Janaka is created. So the certificate of Janaka, that consists of public private key pair, and using the private key it does the sign in process. This certificate is signed by Tidaserat Madhuveltana certificate using the secret key of, or the signing key of this certificate, and this Tidaserat Madhuveltana certificate is signed by Dr. Janakarli Bandara Roduru certificate. So this is a process, but I'm not going to talk details about this. I just wanted to show you an application of sign-in documents digitally, and how to use digital signatures to provide authentication and integrity for documents. So once I send this document to somebody, when he opens it using Adobe Reader, he can just click on this tag and check whether the signature is there, the certificate chain is correct, and everything. But for the proper operation, certificate authority should provide the relevant details available to the people who are going to sign and verify the signatures. Since it is not done properly, this at least once signature has problem message is here. Anyway, this is just to give you an overview about digital, some kind of a example of using digital signatures in our PDF documents. You can search these things in internet, and you can create your own certificates authorities, and then you can open up a server and put the certificate revocation list in there, and then you can properly run as a certificate authority and do this process. Okay, that is just one application, but for our day-to-day message transfers, digital signatures are also used. So now let's discuss about mathematical details of digital signatures. So this the motivation for this thing is obtaining digital signature is one of the major benefits of public key crypto systems. So that means a person who has the sign-in key of or the private key can sign a document, and people who are having the public key or the verification key correspond to that sign-in key can verify the signatures. So digital signatures are deployed widely as part of public key infrastructure. Public key infrastructure is a infrastructure we want to use for using public key cryptography in our real world. So that means use of trusted third party who signs the public key, and because of that trust, anybody can trust that these public keys corresponds or the owns by the people who are claiming to own that. So you can learn about this public infrastructure in your probably in your 3 to 4 course. But if you don't have that in your course, just search in the internet and have a basic idea about public infrastructure. Because of that public infrastructure, we have deployed the SSL TLS protocol suites in our computers, and we obtain certificates from certificate authorities, and we operate this smoothly. In some countries, digital signatures are legally binding in the same way as handwritten signatures. So this is kind of the policy decision. In Sri Lanka as well, we have that kind of legal act there. In most of the countries, especially in Europe, according to Parliament Act, digital signatures are recognized as legal, same as the handwritten signatures. So what I did earlier was putting a digital signature for a document instead of a handwritten signature. Handwritten signature is something like just we sign the document, draw the signature, so kind of like that. But in digital signature, it computes signature generation operation. That means a mathematical operation, like let's say for like RSA encryption, something like that. So that way, signature generation operation is there. That means for a signature algorithm, sign in algorithm, the input is sign in key, the secret key, and the document is, and then using these two, a value is created as a signature and put that thing in the document. So once the document is sent to the other side, or for the verifier can check that the signature using the public key of the signer, and then check whether this signature is exactly created using the same document. So I think you have some kind of understanding about digital signatures, because you have learned about the message authentication codes, MAC, which is the way of creating creating trusted tags for documents, but it is using symmetric key cryptographic concept. But here we use public key cryptographic concept. That means we don't need to share the sign-in keys or verification keys beforehand. Verification keys are just publicly available. Sign-in key is only for the signer. But for message authentication code concept, same key is used for creating the message authentication code tag and for the verification, and that key should be shared between the signer and the verifier beforehand. Okay, so confidentiality and authentication, let's formally discuss this slide again. So up to now we have been studying mainly confidentiality aspects of cryptography. That means how to hide the messages, how to hide the plain text, how to hide the documents, whatever. Only the owner and of the correct key can read or decrypt the messages. So messages are not allowed to the third parties. Only the sender and the receiver is allowed to see that. To achieve that, we use, that is called confidentiality. To achieve that, we use mainly the encryption. And we have seen message authentication codes. Only somebody with the shared secret can generate a valid MAC tag. This provides data integrity and data authentication. So if that message is changed while transferring, the receiver can check it whether it is changed or not. That is called integrity. And authentication, okay, we can see that this kind of tag can be computed for this particular message is only by the person who has the particular key. So that is like kind of providing authentication. Only the authorized person can do that. That implies authentication into the message. Digital signatures use public key cryptography to provide properties of MAC and more. Only the owner of the private key can generate the correct digital signature. The digital signature provide non repudiation security services. A judge can which party formed uh, the digital signature. So once somebody created a digital signature, he can't say he didn't do that, because we know that digital signature can be created by a person who owns the key. So he can't say that, he can't claim that he didn't do that. That's the idea of this last point. Okay, This is a simple comparison between physical and digital signatures. Physical signatures, they are produced by human, same on all document, easy to recognize. But digital signatures produced by machines or computers, or even human can do that, but it is computational thing. And this is a function of a message. That means signature on different documents, different messages can be varied, not the same. But if I sign a document, if I sign 1,000 documents, my signature there is going to be the same. But here, this is a function of a message. Computation is there. Depending on the content of the message or the document, signature is varied. So it requires computer to check. So our physical signatures, we can identify that by looking at it, if you know the person and the signature. But here computers are used to check whether the signature is correct or not. So even the people are not aware of each other, this digital signature checking can be done because it is just a computation. Requires a computer, at least it requires a computation. People can do that by hand, but anyway, some computation is there. Both types of signatures need to be difficult to forge. If I have a really simple signature like just writing my name in plain characters, that is easy to forge. That's why we sign the documents in using very fancy signatures. Only the people who has a training for sign can sign it. So we can expect that the owner of the signature can only write that signature. In this case, this is a mathematical operation and it should be difficult to forge. And these are the elements of digital signatures. A digital signature scheme has three algorithms. One is key generation algorithm. We discussed about key generation algorithms in our AES and RSA and discrete logarithm ciphers, how to generate the public and private key pair. So key generation and signature generation, it is similar to what we discussed about encryption. Some algorithm to generate the signature instead of encryption here. And another algorithm that is having by the verify of this signature, the verification algorithm. When we have signature, we should be able to verify. That's why we have the verification algorithm. This is similar to encryption and decryption operations in our previous lectures. So key generation outputs two keys. One is public key and the other one is private key. The private key is the signature generation key or the sign-in key. We normally use KS, and public key is the verification key. We normally use KV. So normally the idea is we have to keep the sign-in key only with the person who is going to sign the document, but the verification key is public thing. It is publicly available. So we had the word called that public infrastructure. The responsibility of public infrastructure to make these verification keys or the public keys available to the public or the people who needs to use it in a trusted way. So trusted third parties are there. Trusted third parties sign the certificate, and in that certificate that public key or the verification key is included. So once that certificate is shown, anybody can check whether this certificate is correctly signed by the certificate authority, and because of that trust, they will trust the verification keys and the owner of the verification key. The person who claims to own the verification key, he can trust. So that's the idea, or the responsibility of this public infrastructure, to provide the infrastructure which is needed to use this public key cryptography. Only the owner of the sign-in key should be able to generate valid signature, and anybody should be able to use the verification key, signature verification key, to verify the valid signature. And signature generation algorithm, to that, suppose that Alice wishes to generate a signature on a message M. So inputs are the Alice private key, private sign-in key KS, and the message M. Output is the signature S, which is computed as a output of a function SIG. The input parameters are M, the message, and KS, the sign-in key. So I have shown you a simple example about signing a PDF document. So there, the input to the sign-in algorithm, the sign-in algorithm is the message M, that is the document, and KS, that will be chosen by you have seen there's a drop down list, and from that drop down list I have chosen my name, Janaka. So there the sign in key corresponds to me, is chosen from that drop down list and sent to the algorithm. So using the key, the sign in key, and the document itself, that signature is created, and that value is embedded in the tag you saw there. So it should be possible to choose the message as any bit string or any document. The set of all signatures is usually from a set of fixed size. So signature is not going to be arbitrarily long. It should be in the fixed size in a way that it can it is not going to be too long. It's a value, or it's kind of a tag. So we can, so when we send to the document to other party, we send the document itself and the tag, and using the document and tag, verifier can verify whether this tag is valid signature tag. And signature verification algorithm, suppose that Bob wishes to verify a claimed signature S on the message M. Inputs are the public key, public verification key KV of Alice. Alice is the person who signs a document. So verifier should get the Alice's public key to verify the signature, and the message M and the claimed signature S. So what it does is the output is a Boolean value output. So verification will give the message, the message or the document, the signature generated by Alice, and the KV, that is the verification key. So what it does is it checks whether this tag is created using the correct message M. Once that is matching, it outputs true value, otherwise it outputs false value, true or false, whether this signature is created by using the sign-in key KS, which is corresponding to this KV verification key, and the message M. Okay, so when we talk about signatures, there are properties required for verifying function or the signature verification. Correctness should be there and unforgeability is there. So correctness is if S equals sig M and KS, then VER is the verification algorithm, and the parameters M, S, and KV equals true for any matching sign-in verification keys. So it should be correct. If there is a correctly created signature, message, and the message pair using the verification key KV, it should be able to correctly verify the signature. Should be always correctly verifiable. And unforgeability is it is completely infeasible or impossible for anyone without KS to construct a signature M, signature S for a message M such that verification algorithm outputs true value when it is computed. So that means without having the sign-in key KS, it is completely impossible to generate a valid signature in a way that it is going to be verified by the corresponding verification key KV. And if the message is altered or changed or different message is used, using that message also, if the verification operation is done, value should be false. And note that the signing algorithm SIG may be randomized so that there are many possible signatures for a single message. Otherwise, by having a message and signature pairs as a dictionary, and person can forge using that dictionary. So it is required that the signature generation algorithm should be a randomized, or what we call probabilistic algorithm. So having the same message and the sign-in key KS and M, by running this signature generation algorithm, the output can be different. We run the same the signature generation algorithm for the same message M and KS, let's say for 3 times. So 3 signatures will be generated. So this is a probabilistic algorithm. That is the ideal case. Should be a probabilistic algorithm. But the verification, it should not be probabilistic. It is deterministic. Once it is a correctly created signature, it should always output true, otherwise false. It should be deterministic, but signature generation should be a probabilistic algorithm or randomized algorithm, not deterministic. So when I use the words, I try to emphasize as much as possible to make you familiar with these words. Okay, and security goals. What are the security goals? So if you are working on digital signatures and signature schemes, designing signature schemes, this kind of information is useful for you. The attacker may try to break a digital signature scheme in several ways. There are several ways of breaking the signature scheme. That is according to what, like, how we define matters. So key recovery. The attacker attempts to recover the private sign-in key from the public verification key and some signatures. If we say that breaking our signature scheme means key recovery, that is like what we define as breaking the signature scheme. If we say that, that should be key recovery. That means the attacker should be able to get the private sign-in key from the public key and some signatures, signature message pairs, something like that. And other thing is selective forgery. The attacker chooses a message and attempts to obtain signature on that message. So attacker has the verification key, that is because it is a public value, and selective forgery means it is not hard as key recovery, but attacker is just trying to make a signature just for one message. The attacker chooses a message by himself. He chooses the message. He says, okay, I'm going to, what I want to do is I want to create the legitimate signature for this particular message and attempt to obtain the signature on that message. That is called selective forgery. No matter he can't create signatures for other messages. The idea is like, let's say, uh, I have uh, I have failed my degree. So when I ask for a transcript, in the transcript it says Jana Kalawatgoda failed. So what I want to do is I want to say a statement called Jana Kalawatgoda passed, and having that in my transcript. So what I want to do is I want to create a legitimate signature on that message only, not other messages, not my attendance, not on my not anything, but only on the message of my transcript. So that is called selective forgery. I choose a message which I want, and I'm trying to create a signature, legitimate signature on that message. That is called selective forgery. If I can do that as an attacker, I am successful. I don't need to get the sign-in key, or I don't need to sign any other message, but I only need to sign the message I wanted. That's the only thing. Another thing is existential forgery. The attacker attempts to forge a signature on any message not previously signed. It could be meaningless message. So it is the when you can, okay, the existential forgery means that attacker is going to create or the forge a signature on any message. In the previous case it is like the message on my transcript. I want to say Jana Kalawatgoda passed, but here not like that. I don't need any particular message, but any message I can easily forge a signature. That's my target. It could be meaningless message, random set of characters message. When you look at these ways, or three, let's say, 3 points, you can see the last point, existential forgery, is the easiest way that attacker can do that. Attacker just try to create a signature on any message, just one message, but anything. But selective forgery, attacker chooses a particular message and try to forge a signature on that. That is little bit difficult than the existential forgery. And key recovery is attacker tries to get the key. Once attacker get the key, attacker can sign any message. Any message. It is hard. Recovering the key is hard. Selective forgery, it is little bit easy than key recovery, and existential forgery is the easiest. So key recovery is the strongest of these attacks. Modern digital signatures are considered secure only if they can resist all these attacks. So in modern signature schemes, we say that they should they should provide security against these 3 kinds of attacks. Even existential forgery should be prevented. So a signature scheme which is secure against existential forgery means it is high secure, because even a easiest task easiest task like easiest way of attacking is not allowed there. A signature scheme which is not secure against existential forgery and selective forgery, but let's say it is secure in secure against key recovery attacks. So that means that signature scheme is not very strong, because it is only secure against the most difficult attack, but easy attacks, it is vulnerable. So that signature scheme is not going to be very secure. If the signature scheme should be very secure, even the easiest task, easiest way of attacking should be prevented. And digital certificates, we have discussed this thing on and off in previous slides. So in order to trust a digital signature, it is essential that the verifier is confident of having the correct binding between the public key and its owner. If I say this is my public key, how can you trust it if you don't know me? If you know me, you can trust, okay, this person is saying this is his public key, so it should be correct. If you don't know me, I can say I am the head of the department and this is my public key. If you don't know me, you can't trust. If you know me, if I say like that, you know that I am not the head of the department and you are not going to trust my public key. So the binding between the public key and the owner should be confidently communicated to the verifier. So what we can do, it's like, let's say I'm saying I'm a lecturer in the department. If I say that, if you know me, you trust it. Let's say I'm very new person, you don't know me, and I come to your class and say I'm a lecturer in the department. How can you trust me? You can't trust me just by seeing me. So if I show a certificate or a letter signed by the head of the department, you know him, you trust him. If I show that, okay, I am a new lecturer in this department, this is the certificate issued by the head of the department, you are going to trust me from that point onwards. And if I say this is my public key, please use this, you will use it because you trust the signature or the letter from the head of the department. And because of that trust, you start trusting me from that point onward. So that is kind of like providing the transferring or the communicating the confident of having the correct binding between the public key of the owner and the person who claims to own that. So normally this is achieved through digital certificates. Digital certificate is kind of a certificate that is again a digital value, similar to what I say, the letter from the head of the department. So which contains a public key and owner identity. So in that letter, it says owner of the identity is Jana Kalawathugoda and public key of Jana Kalawathugoda is mentioned in that letter, and that letter is signed by the head of the department. You trust the head of the department and his signature, and because of that you are going to trust me and my public key, and from that point onward you are identifying me as Jana Kalawathugoda. So certificates are usually include other information such as signature algorithm, the validity period. Okay, in that letter, head of the department can say, this person is, let's say I'm a contract basis person. This person is going to be a lecturer in the department for next 2 years. So after 2 years, you can reject me because validity period is expired. The certificate is itself digitally signed by party trusted by the certificate verifier. So certificate verifier. So you are, in that example I mentioned, you are the certificate verifier. You are going to verify. So you are going to trust the third party, that is the head of the department. So you trust the third party, and because of that trust, you are going to accept the certificate I show to you. That certificate mention my name, my public key, and validity period like information. Certificates play a central role in key management for public key infrastructure. So public key infrastructure is this kind of infrastructure that facilitates to use the public key cryptography. Trusted third parties there, digital certificates are there. You have the trust between yourself and the certificate authority. Likewise, so how in our this simple example, you trust the head of the department because that information is communicated to you somehow. You are going to trust that. But how do you trust a trusted certificate authorities in your internet communication? How do you trust the signature of the certificate authority? It is again a signature coming from outside. How are you going to trust it? In our computer systems, in operating systems, these kind of information, the information about certificate authorities are embedded or the provided by the operating systems, by the manufacturers. Or when you download web browsers from, let's say, like Google Chrome, they also provide information about the trusted third parties. When you download Adobe, Adobe will also provide list of trusted authorities, trusted third parties from its software itself. Because of that information coming from the manufacturers, or the manufacturers of the hardware, or manufacturers of the softwares, your computer system is going to trust that, because that information is implemented in your systems. Because of that, anything signed by those trusted third parties will be recognized by your applications. So all the private certificates and anything which are signed by those trusted authorities, trusted third parties, will be recognized by your systems. That's the idea. So this is not simple. This is widely established big thing, big infrastructure. And in signature schemes, we need one-way functions. So what are the one-way functions? So the public key operations are computationally costly, and message sign may be very large. So message to sign can be very large. Like it can be a document, PDF document of several pages, maybe 100 or 1,000 pages. So message to be signed may be very large, and public key operations are very costly. So because of that, there is common to use a hash function as a part of signature algorithm. So the idea of the hash function is, it's a function that once an input is given, it outputs a value of fixed size that is going to be smaller than 1,000-page PDF file. So hash function is there. It's a one-way function. Once you have a document or a big message, you can input it as a parameter to the hash function, and hash function will compute a hash tag. That tag is fixed size thing. It's one-way function. By using the tag, you can't go back to the document. You can't go reverse. It's one-way function. The sign-in algorithm becomes SIG. Instead of the message, we put the hash of the message into the as a parameter to the sign-in algorithm. That's a common practice. Not just the message, but the hash of the message. And the message M is stored together with the S. So message is stored together with the sign, the signature S. Once it goes to the verifier, verifier can first create the hash of the message M, because hash is a public function, one-way function, and can compute the HM hashtag, and then he can do the verification, and verification gives back the hash of the message, and then computes whether that hash of the message came by the verification function is going to be equal with the hash value he created using the message M he gets from the sender. And then if both of them are matching, then it outputs the true, otherwise false. So hashing is to make this signature generation and verification little bit efficient, because it's a fixed size message, fixed size value, and signature generation is going to be not that expensive because of that fixed size length. And one-way functions, we have to little bit learn about one-way functions when we have this topic. One-way function H is a public function such that H is simple and fast to compute. H takes as input a message M of arbitrary length, any length, arbitrary means any, and outputs a message digest or the tag HM, tag of the message using the hash function. Message digest, that's what we call in output of a hash function in cryptography. It is of fixed length, and S is hard to invert, hard to reverse. Just by having the message digest, it is not possible to compute the message. That's one-way function. And when we talk about hash functions, this thing is a little bit more theoretical. You may not need to follow that if you are not very interested. So these properties are expected in hash functions. One is collision resistance, second pre-image resistant, and one-way. Collision resistant means it should be infeasible to find any two different values x1 and x2 with hash of x1 equals hash of x2. So it should be infeasible or hard to find two different values x1 and x2 such that hash of x1 equals hash of x2. If that happens, that means if it is easy, that means we can simply use hash functions in our signature schemes, because signature is generated using the hash value or the message digest, but message digest can be belongs to two different messages. So this should be a infeasible or very hard thing. And second, pre-image resistant. Given x value, it should x1, it should be infeasible to find different value x2 with h of x1 equals h of x2. So it looks similar to the first thing, but there is a difference. The difference is, in the first case, the collision resistant find two different values having this property. But second pre-image resistant is, it's like given a value x1, it should be infeasible to find a different value x2. So in the first case, the idea is, the task is to get any two values and show this thing. It's easy. Compared to the second case, it's easy. Like, you can have any two values. Any two values means you can pick values which satisfies the requirement h of x1, h of x2, both are equal, and to satisfy that thing you can find any two values x1 and x2. But in the second pre-image resistance, the task is you are given a value x1. You can't find two values by your own satisfying the condition, but you are given a value x1. It is little bit hard. So it's like let's say, this is not a very matching example, but anyway, let's say I ask you to find any two flowers in white color. Then you can find someone picture and earlier white color flowers, and once you show that to me, you are done. You achieved your task. That's kind of collision resistant. But the second task, the second pre-image resistant, there I ask, first I give you a let's say a flower with let's say like a white color flower, and then ask you to find another white color flower with the same size, or let's say same weight or something like that. So you can't just come up with, if I give you someone picture, you can't come up with earlier. You have to find a flower which has the same weight as someone picture or same size as someone picture. So your task is hard. That's the idea of second pre-image resistant. Collision resistance is little bit easier. Second pre-image resistant is more harder. And one way, given a value y, it should be infeasible to find the input with h of x equals y. That's we discussed in our previous slide as well. Attacker who can break second pre-image resistance can also break collision resistance. So I mentioned that collision resistance is little bit easier than second pre-image resistance. You are given a value and asked to find a value matching with that, hash is matching with that. So second pre-image resistance is hard task. If anybody who can break the second pre-image resistant, he can break the collision resistant as well. So these properties are expected in hash functions. Otherwise, we can't use them in signature schemes. And there's another thing called birthday paradox. Let's have a little bit of discussion about this thing and talk about the relevance of this in our thing. In a group of 23 randomly chosen people, the probability that at least two have the same birthday is over 0.5. In general, if we choose around m square root values from a set of size m, the probability of getting two values the same is around this much, 0.5. Suppose that a hash function h has input size of k bits. If h is regarded as random function, then 2 to the power k divided by 2 trials are enough to find a collision with probability around 0.5. Today, 2 to the power 80 trials would be considered infeasible because of That is kind of a brute force that is infeasible. So therefore, in order to satisfy collision resistance, hash function should have output of at least 160 bits. So if you have a 160 bit message digest from a hash function, we can say we can eliminate collision resistance, because to find a collision it is needed to do 2 to the power 80 trials. It is impossible or infeasible according to the computational powers we have at the moment. It's kind of a brute force of 80 bits. There are many hash algorithm families. One is MD Hash Family, which is used throughout the 1990s. And then the new standard came into the picture, which is SHA, Secure Hash Family. In that family, there are many other algorithms like complex hash algorithms. Currently, the standard is SHA-256, which uses the 256-bit output as the message digest. Earlier ones are SHA-0, which is the first version of hash family, and both SHA-0 and SHA-1 have 160-bit outputs, and later on, to make it secondary image resistant and collision resistant, it becomes like more lengthy message digests. So that's about hash algorithms, the use of hash algorithms as 1A functions in signature schemes. And details about hash functions are in these slides, so you can follow them. Now let's look at how this signature, like the parameter generation, happens in RSA signature scheme. So this is similar to the RSA encryption scheme we used. We have learned in our previous lecture. So RSA key generation, the signature keys are generated in the same way as RSA encryption keys. We know that. So public verification key is value E and N, where N is P times Q for large primes P and Q, and the private sign-in key is D, such that E times D mod pi N equals 1. So one-way hash function H is also required and should be fixed. Should be a fixed public parameter of the signature scheme. That means the hash function should be a public function. So this is the signature operation, signature generation. There we input the message M, the modulus N, and the private the sign-in key D. So first hash of the message is computed, and any large message is shrinked into the message digest. If it is SHA-0 or SHA-1, that can be 160 bits output, or if it is SHA-256, that is going to be 256 bits output, or if it is SHA-512, 512 bit output. And then on that output, that fixed length message digest, that output to the power D mod N computation is happen. The value D is the private sign-in key. And the output is a pair M and the signature S, message M and the signature S. Signature verification, in there, both the M and S values are used, and the public key E value, that is going to be the verification key, and the modulus N is used as parameters. So it computes So first compute the hash h prime value, which is going to be the hash of message m. The message m it receives from the sender, the m value. From using that, because the hash function is a public function, compute the hash of that message and keep that value, and then verify. Then what we do is s is the signature, comes from the sender. S to the power e mod n is computed, and that value is taken. And now we do the comparison between the computed hash value of the message and uh, the, the value we got from the signature verification. If these two values are the same, then signature is true. If it is false, if they are not matching, that means signature is a false value. That's how the signature generation and verifications happens in RSA signature operation. And then there is another signature scheme which is based on El-Gamal scheme. So in RSA scheme, we know that it is based on the uh, integer factorization problem. And when it comes to the El-Gamal based signature scheme, that is using the discrete logarithm problem as underlying hardness assumption. So there, let P be the large prime with generator G from an integer multiplicative group. We choose a large prime number P and having the generator G, and then private sign-in key X is randomly choose in a way that it is between 0 and P minus 1. And then the public key is Y, which is G to the power X. G is the public parameter, which is the generator of the multiplicative group, and G to the power X mod P. So value P, G and Y are public knowledge, and X is the secret value, which is used as the sign-in key. And suppose Alice wants to sign a value M, which is an integer between 0 and P minus 1. So what Alice has to do is, Alice randomly picks a value K such that GCD, or the greatest common divisor of K and P minus 1 equals 1. That means K and P are relatively prime values. And then computes R in a way that G to the power K mod P equals R. So then Alice solves M congruent X times R plus Ks mod P minus 1 for S by computing S equals K inverse M minus XR mod P minus 1. You can take a piece of paper and do this computation by yourself, and you can verify this is working. And finally, Alice outputs a triple, which is M, R and S. So this R value is used to, we know that to make this a randomized algorithm, or probabilistic signature generation algorithm. So M is the message, S is the signature, and R is the randomly a value which is based on the randomly picked K value. The K is used as the value to randomize the algorithm, or make it a probabilistic signature generation. And in signature verification, Bob verifies, once Bob receives the message coming from Alice, G to the power M congruent Y to the power R, R to the power S. R is coming with Alice's message, S is coming with Alice's message, Y is the public key of Alice, and P is a public parameter, and then he computes this value, G to the power M. So if this is going to be g to the power m, g is the generator of the group, it is public parameter, m is the message, and if these two values are matching, g to the power m equals y to the power r to the power s mod p, then Bob can verify the signature is correct. Take a piece of paper and do this computation so you can verify it. So since I have used the term randomized algorithm here again, randomized or the probabilistic algorithm, we know that here using a random value k, we can make the signature generation randomized. When it comes to the RSA signature generation, we have to use some kind of padding there. So then we have another thing called digital signature algorithm, DSA, which is published by NIST, that means National Institute for Standards and Technology, as far as I know, in 1994, and this is also known as FIBS PUB 186. So this DSA algorithm is based on El-Gamal signature scheme, but not really the El-Gamal, but it has a slight change, but based on the El-Gamal signature scheme. That means it is based on the discrete logarithm hardness assumption. So this is simpler to calculations due to restricting the key and message spaces, and designed for use with secure hash standard SHA, which is also published by NIST, SHA family, and avoid some attacks that El-Gamal signature may vulnerable to. So this is improvement of digital signature, the El-Gamal signature scheme, and this is standardized. And even now you can see when you look at the your secure internet connections, SSL TLS protocol suites use this DSA algorithm for signatures. So I'm not going to talk about the differences between this and El-Gamal, but in these slides you can have that information. So these are the differences, and keep in mind that DSA algorithm is a improvement or the variation of El-Gamal signature algorithm, eliminating some attacks on El-Gamal as well as making it more efficient to compute. So all the information about DSA key generation, the signature generation and verification is here very clearly. And these are the DSA and DSA versus El-Gamal. The verification equation is same as the El-Gamal signature scheme, except that all exponents are reduced to modulo Q, and the final result is also reduced to modulo Q, that is to make the computation more efficient. The complexity of signature generation is now mainly just one exponentiation with the short exponent between 160 and 256 bits to make it efficient to compute, and signature verification requires two such short exponentiations. That means computation of to the power computation. The signature size is only twice the length of Q, 360 bits when N is 160. So this modification is done to make El-Gamal, so the DSA computation, efficient to be used for internet communications. So this is all I wanted to discuss about signature schemes. So there are more information in these slides. You can take a piece of paper and do the computations by yourself and verify and digest that knowledge. And you can see that some of the details I have discussed here are too theoretical and maybe a little bit hard to understand at first, but I intentionally did that and grabbed this final topic little longer to give you more exposure to the terminologies and concepts we have in cryptography. And also so I'm finishing this cryptography lectures after this one, and I will give you an assignment to do some computations of about signature schemes, so you can practice these questions to prepare for your exams. And I'm hoping to give you another little longer assignment based on a research paper, just to read the research paper and identify the uh, details, some sections, and do some kind of summarization, that sort of thing, giving you a longer deadline. So that is to give you more exposure if you are interested in cryptography. And so as a summary, I can say that public key cryptography is for mainly two purposes. One is to provide the confidentiality using without sharing the secret keys beforehand, and the other purpose is to provide authentication and integrity, that is the signature schemes. In symmetric key way, we used message authentication codes. The main difference between public key cryptography and symmetric key cryptography is, in symmetric key cryptography we have to share the secret key beforehand, but in public key cryptography we do not have to do that, but instead we have to have a well established public key infrastructure uh, available. Okay, so I am finishing the lecture now. Thank you very much.